In the next section, we'll look at a few relatively simple solutions for this problem. They will not achieve the optimal preprocessing and query time yet, but there are building blocks that we'll use. And also, they're much easier to understand, so we'll start with those. First, a few trivial things you can do. Very easy. Showing the extremes of the scale. One option is you do nothing at preprocessing time, which means at query time, you have to do all the work. All the work means, well, we have to find the minimum in some range. So we just walk through and keep track of the current smallest element. If we do that, say, from right to left, we can keep track of the last occurrence. That's the leftmost. Different options. And then you need time proportional to the length of the range that you're looking at. But in the worst case, the range that you're looking at is the entire array. I can always query with 1 and n, or 0 and n minus 1. And then the query time for the worst case is linear. And that's not particularly useful. That's too slow, but it's an option, right? And we have no pre-processing time. I could basically have said 0, but order 1 is an upper bound is, of course, also true. The other extreme end is we do all the possible work at pre-processing time, and at query time, we just read off the stored result. How would that look like? I can store a 2D array m for minimum, which just stores in mij. It stores the answer to rmqij. And then the query is trivial. Query just says return rmqij, return mij. But the pre-processing is super slow now. If I do it really stupidly, I could say for I from 0 to n, and then for j from, I guess it can't start before I. Okay, we can have the same. Now I have to compute the minimum. So we could say, let's spell this out, doesn't hurt. And then I probably want to remember the position rather. Is I. And then we do a loop for from I to j. And if my previous minimum is no longer the minimum, so if I compare it with ak, and ak is strictly smaller, then I update my entry a. That would be one easy solution. I have to store this. Okay, gets a bit running out of space here. That would be simple code to compute all the values mij up front. And this takes cubic time because I have one loop that takes n iterations, another loop that takes n iterations, and then a third loop in the middle that in the worst case takes length n. And you can again prove that asymptotically it's cubic. Can you do better? Can you somehow speed that code up a bit? You can massively speed it up in this inner loop because we're really throwing away all the knowledge from past rounds. If you iterate over the subproblems in a slightly smarter way, then how do you get from mij to mij plus 1, for example? So I make the range 1 bigger at the right end. Now, if that's my previous range, that's the new element, I, j plus 1. In the range from I to j, there's some minimum somewhere. Now, if I add one more element at the end, there's two options for the minimum of the new entire range. It could either be here, or it can be this element. But it cannot be any of the other elements, because these were already bigger than that element. So I can make the next bigger range and find its minimum in constant time by just comparing these two options. Right? So that's how we get the running time down to quadratic again, which is now the size of this array m. And we have to at least fill that, so there's no way around it. Maybe it's worth spelling out some code for that. So all we have to do is make sure we iterate over m by order of the length of the range. So we can have anything between 1 and n elements. Then we iterate over the range. It can start at 0, anywhere up to n minus l. And then I guess we can do a case distinction. If the range is just 1, then I'll store at I, mi, I plus l. I'll store I. That's the index of the minimum if I just have a single element. And otherwise, there's a smaller one. So I can take my I and I plus L minus 1. We'll use that a few times. Let me give that a name. So editing the code on the fly is maybe dangerous. So one option is this. The other option is j plus 1. I have two positions that I have to check: the position of the previous minimum and the new position that I'm adding into the range. And so again, running out of space, let's move it a bit up here. Okay, I can cheat a little bit. So I'm checking now if A of A is less or equal A of B. Then I keep A. And otherwise I use B. Okay. So with this code, we can solve all the pre-processing in quadratic time. So I have two loops. This one runs n times, this one runs n times, and everything I do inside of here is constant time. It's just a fixed number of instructions. Okay, but zooming out again, that gives us order n squared pre-processing time and then constant query time. So the constant query time is great, but we're wasting a lot of space. And because we have to fill the table, even if we're smart about computing the next minimum, we still have to write to the output. So we won't be able to improve upon this n squared running time for pre-processing unless we don't store as much data. Okay, how can we store less? The idea is to do what we've done in the trivial pre-processing everything step, but don't remember as much. Actually remember very, very few of the entries. And what works here is only remember entries where the range that we cover has a length that's a power of 2. Okay. First of all, immediately from that, we can bound the number of entries in that table, because the overall length of the range is never more than n, so there's never more than log n powers of 2 below n. And so we have for each starting point at most log n entries, which is much smaller than n squared. And it's convenient to store those. Instead of giving the start and end index, we just give the start index and then the power of 2 for the length. Then you have it back in a nice contiguous piece of memory. Now that's fine. Suppose we can compute those answers and store them. How is that helpful for queries? We can no longer just return m of I and j. I might not have stored the answer, right? Luckily, I can still reconstruct the answer. I cannot immediately output the answer, but I can reconstruct the answer in constant time. And the reason for that is as follows. No matter how long your actual query range is, in this case, it goes from 5 to 18. So I guess it's what, 14 elements? That's not a power of 2, right? So I don't have an entry in my table that directly tells me for this range where's the minimum. But what I always have is a value k that's, a value k, so that 2 to the k is between the length of my query and half of that. That always exists by definition. And so I can cover my red range by 2 ranges that have a power of 2 as length. And it's always so that they at least touch, or actually they always overlap by 1, because I could have made this strictly less. Okay, the ranges definitely at least touch. So they cover the entire red range. And so where's the minimum in the whole red range? Well, we don't know, but if there's a minimum in the blue range here and a minimum in the green range there, it has to be one of the two. If it was any other element, then there's a range where they are together with that element, and the answer in that range contradicts, for example, I mean, the 10 is definitely not the minimum. I should have circled the real minima, which are marked by the arrows. Sorry, that was more confusing than helpful, maybe. Why can this element never be a minimum? Well, if it was, then it would have had to be the minimum also in the green range, but RMQ for the green range said, no, here's the minimum. So the overall RMQ in the range from I to j, from 5 to 18, is one of those two positions, whichever gives the smaller value. Again, with ties broken to the left as before. So I ask these two subqueries, which have a length of power of 2. So these are just stored. So, okay, I don't know if I can fit that here. That one's stored in m prime ik, and the green one's stored in m prime j minus 2 to the k plus 1. A bit less nice, but still it's just some number that you can compute. So these two elements you can look up. That's two indices in the array, maybe 10 and 17. And then you do this check. You find the values in A, do one comparison. So this notation argmin just means the position where the minimum is attained among those two options. So you would have code that's like this. If A of A is less than A of B, then the result is A, otherwise it's B. So that's how you get by with just n log n entries instead of n squared. The pre-processing can be done similarly to what we've done for the stupid version where you compute all answers. Because if you go from a range I up to I plus 2 to the k minus 1, and now you want to go to that with the next largest range, so the power of 2, one bigger. What does that look like? This is one range, and then you have another one of the same length, and that gives you that range. So you have the same situation as here. You have a blue part on the left, and you have a green part on the right. The minimum of the entire range has to be an element from somewhere in the range, so it's either the minimum of the blue part or the minimum of the green part. And both of these you have computed because they again have a power of 2 as length. So you can do with a similar trick. You look up the smaller ones, compare which is smaller, and that gives you the result for the long range. So as before, you can fill each entry in our table in constant time. So the overall pre-processing time is n log n for the size of the table. And query time is still constant. It's a different constant. It's slightly slower than before. We can't just look up one entry in an array. Instead, we have to look up 2 entries in an array and do one comparison, but still constant time. Okay, so far so good. That's about as far as you get with simple tricks like this. So you can try to think about how to make further improvements. But I'm not aware of a solution that gets there. If you're just trying to do that approach, somehow get rid of even more elements, it doesn't seem to work. So instead, you need some fundamental different approach to solving that problem.